Welcome to the NPTEL MOOC on Discrete Mathematics. This is the third lecture on set theory. At the end of the last lecture, we were seeing how the theory of integers could be embedded in set theory. Our idea was this: an ordered pair Mn of natural numbers should stand for the integer m minus n. Then the ordered pair 2, 3 would stand for minus 1, the ordered pair 3, 2 would stand for plus 1. So what we do is this: we define a relation tilde on n cross n, where n is a set of natural numbers. The idea is that ordered pairs mn and pq would be in relation tilde with each other if m minus n equal to p minus q. But since natural numbers are not closed under subtraction, we essentially capture the same by using addition. We write m plus q equals n plus p. We know that this would be the case precisely when m minus n is equal to p minus q, and m plus q and n plus p are both well-defined natural numbers. So we achieve the same end. We define the relationship tilde in this fashion. For the order pairs mn and pq, mn is in relation tilde with pq precisely when m plus q is equal to n plus p. Then we can see that tilde is an equivalence relation because it is reflexive, symmetric and transitive. Then using this, we can express integers in this fashion. For example, the integer 2, which we denote 2z to distinguish it from the natural number 2, would be the equivalence class to which 20 belongs. So this equivalence class would contain 20, 31, 42, 1 minus 1, 0 minus 2, etc. All these points would lie on the straight line with slope 1 and passing through 0 minus 2. Similarly, the integer minus 3, which we denote minus 3 subscript z to distinguish it from the natural number 3, would be the equivalence class containing the ordered pair 0, 3. All the integral points belonging to the straight line with slope 1 and passing through 0, 3 will also belong to the same equivalence class. So all these points are equivalent under the relation tilde. So that is how we define the integers. Now comes the question: how do we define the integral operators? For example, addition. Addition of integers, which we denote plus with a subscript z to distinguish it from addition of natural numbers. Addition of integers is defined in this manner: ordered pairs, the equivalence class containing ordered pair mn under the relation tilde. This is an integer. This added to the integer which is defined by the equivalence class to which ordered pair pq belongs. So these two are integers. This is one integer and this is another integer. This integer is supposed to correspond to m minus n, and this is supposed to correspond to p minus q, where m, n, p, q are all natural numbers. Then their sum ought to correspond to the integer m minus n plus p minus q, which could be written as m plus p minus n plus q. But the equivalence class under tilde to which ordered pairs of this sort will belong would be clearly this. Therefore, this ought to be the result of the addition we have here. That is, when integers corresponding to the equivalence classes mn under tilde and pq under tilde are added, we should get the equivalence class that corresponds to the ordered pair m plus p n plus q. If this is how we define addition, then it would indeed be consistent with the notion that we have. The notion that we have is that the equivalence class corresponding to ordered pair Mn stands for the integer m minus n. That is indeed the case under addition defined in this manner. Then we can see that this addition is commutative. Changing the order of the arguments will not change the result. We will get exactly the same equivalence class. It is associative. It has an identity. This is the identity of the addition operation we have defined. Remember, 0z is the equivalence class to which, for example, 1 1 belongs. Each integer, you can see, has an additive inverse. Under addition, which is defined in this manner, we can see that when this integer is added to this integer, what we get is which is 0. Therefore, every integer has an additive inverse. In short, the integers that we have defined along with the operator plus z form an abelian group. You would recall the definition from the module on algebra. It's clear that z plus z is an abelian group. The other operator that we want to define on integers is multiplication. Let us denote multiplication by star z. Multiplication would be defined in this manner. When we multiply integer m minus n and p minus q, we would like the result to be mp plus nq minus mq minus np. So, with this intuitive understanding, we can define the result of the multiplication as the equivalence class containing the ordered pair mp plus nq. This addition is the addition over natural numbers. So, this is how we should define multiplication of integers that correspond to equivalence classes containing ordered pair mn and ordered pair pq under tilde. So, if multiplication is defined in this manner, it will be consistent with our intuitive notion of integer multiplication. So, you can verify that this multiplication operator is commutative, associative, it distributes over plus z, and 1z is the identity of this multiplication. Moreover, you can also show that whenever a multiplied by b for two integers a and b is 0, either a is 0, this is of course 0z, the integer 0, either a is 0 or b is 0. All this is exactly consistent with our definition of integers. Therefore, what we have understood is that this definition of integers, along with the definitions of addition of integers and multiplication of integers, behave exactly the way the integers are supposed to behave. In other words, this definition of integers, along with the addition operation, the multiplication operation, the special number 0 and 1, which function as the identities of addition and multiplication respectively, is an integral domain. Again, recall the definition from the module on algebra. Therefore, the definition of integers work exactly the way we want. So this way of defining integers as set theoretic constructs achieves what we wanted to. The theory of integers is now embedded in set theory. The less than relation on integers is defined as follows. We want to say that integer corresponding to the ordered pair Mn is less than the integer corresponding to the ordered pair Pq when would we want to say this? Intuitively, we would want to say this precisely when m minus n is less than p minus q. That is, integer m minus n is less than p minus q, which would be the case when m plus q is less than p plus n. Since we do not want to use subtraction because natural numbers are not closed under subtraction, we try to rewrite the same condition using addition. Therefore, this is what we achieve. So, we would be able to say this precisely when the natural number m plus q belongs to p plus n. This condition would hold precisely when natural number m plus q is less than natural number p plus n. The way we have defined natural numbers using sets, we know that natural number 0 belongs to natural number 1, which belongs to natural number 2, and so on. Recall that 0 corresponded to the empty set, 1 corresponded to the singleton containing the empty set, 2 corresponded to the two-member set containing these, 3 corresponded to the three-member set containing these, and so on. So you can see that 0 belongs to 1, which belongs to 2, which belongs to 3, and so on. So you could say n belongs to p precisely when you want to say that n less than p. So that is what we have done here. We say that the integer corresponding to the equivalence class containing the ordered pair Mn is less than the integer corresponding to the equivalence class containing the ordered pair Pq precisely when the natural number m plus q belongs to the natural number p plus n. A word about the relation less than. A binary relation R on a set A is a linear ordering. If R is transitive on A, and satisfies trichotomy. What is trichotomy? R satisfies trichotomy on A if and only if for every x and y in A, exactly one of the following hold. Either x or y holds, x is equal to y, or y or x holds. If this is the case, then we say that R is a trichotomy. So a binary relation R on A is a linear ordering precisely when R is transitive and satisfies trichotomy. So you can see that the less than relation on natural numbers is a trichotomy. For example, either x less than y or y less than x, or x is equal to y, and the less than relation is transitive. So using the less than relation on natural numbers, we have now defined the less than relation on integers. So with these basic definitions, we see that the theory of integers that we have evolved behaves exactly according to our intuitive understanding of integers. So that is why we say that the theory of integers could be embedded in set theory. Now let us see how the theory of rational numbers can be embedded in set theory. So we have now defined the set of integers z. Using z, let us define z prime as z minus integer 0. Then we define a new relation which we denote like this. This new relation is defined as follows. We said that ordered pair stands in this relation to C by D, to ordered pair CD. So mind you, these are ordered pairs from Z cross Z prime. Z prime doesn't contain 0z, therefore B and D cannot be zeros. So our idea is that these ordered pairs should stand for A by B and C by D respectively. But since on integers the division operation is not defined, that is, integers are not closed under the division operation, so we don't want to mention division here. But what we want to say is that A by B is equal to C by D. That is, we want to say that ordered pair AB and ordered pair CD stand in this relation precisely when the fraction A by B is equal to the fraction C by D. These two fractions are well defined because B and D are non-zero. But this would be the case precisely when A into D equals B into C. So that is precisely what we are going to say. We would say that ordered pair AB stands in this relation to ordered pair CD precisely when A multiplied by D, we use the integer multiplication, is the same as B multiplied by C. So this is how we define the relationship. And then on this relationship we consider a set of equivalence clauses. We define the set of rational numbers which we define as Q as the equivalence clause the set of equivalence clauses of Z cross Z prime under the relation we have just defined. What does this mean? It means that the rational number 2 This is of course 2 by 1. This corresponds to the equivalence class containing the ordered pair 2, 1. Under this relation, this would of course contain four two, 6 3, 8 4 and so on. So this set is defined as the rational number 2. This set will stand for the rational number 2. So exactly as we did before, we will now equate every rational number to a set. So in particular, on the xy plane, where would these points fall? We have 2 1 here, 4 2 here, and so on. So these points would fall on a line with slope 1 by 2 passing through the origin. So we consider all integral grid points that fall on the line with slope 1 by 2 and passing through the origin. These points would correspond to integer rational number 2. All the integral points falling on this line would form the set which is defined as rational number 2. Then let us consider minus 1 by 3. The rational number minus 1 by 3. This would correspond to the equivalence class containing the ordered pair minus 1 by 3 under this relationship. If you enumerate some of the ordered pairs belonging to this, we would have minus 1 by 3, 1 minus 3, minus 2 by 6, 2 minus 6 and so on. These would correspond to the integral points on the line passing through the origin and of slope minus 3. That is, if you plot, you consider 0 0 here, we want minus 1 by 3 and 1 minus 3 to be on the line. So it would pass through these 2 points. So this has a slope of minus 3, and every integral grid point falling on this line would form the set, would be in the set, which is defined as minus of 1 by 3, the rational number minus 1 by 3. So in this sense, we define every rational number as a set. So under this definition, every rational number is defined as a set. So this is analogous to what we did earlier. We defined every natural number as a set, first of all. Then we defined every integer as a set. And now we define every rational number as a set as well. Then how would we define addition and multiplication of rational numbers? First, we want to define addition of rational numbers. So let us consider 2 rational numbers. That correspond to equivalence classes containing ordered pair AB and CD respectively. These intuitively correspond to A by B and C by D. So, our requirement is this: we want to add the fractions A by B and C by D, add the rational numbers A by B and C by D. We know that when we add them together, we will get BD in the denominator and AD plus BC in the numerator. This would correspond to the ordered pair AD plus BC comma BD. So, the equivalence class containing this ordered pair under the relationship we have defined should be the result of the addition. So, if the addition of rational numbers is defined in this manner, it would exactly correspond to the intuition we have. So, that is how we will define the addition of natural numbers, and then we can see that according to this definition, addition is commutative, associative, rational number Q is the identity, rational number 0Q corresponds to this equivalence class, 0 divided by a non-zero integer. This is the identity of the addition, as you can readily verify, and we can also see that this addition is invertible. That is, for all A belonging to Q, there exists a B in Q such that A and B added using this addition operator will render 0Q. So, every rational number has an additive inverse. Therefore, we have that the set of rational numbers along with the addition operation is an abelian group, exactly as it was in the case of integers. Now, coming to multiplication, you can readily work out how multiplication has to be defined. We consider multiplication of rational numbers. So, let us say we want to multiply the rational numbers corresponding to the equivalence class containing ordered pair AB and the rational number corresponding to the equivalence class containing the ordered pair CD. These two are what we want to multiply. These equivalence classes respectively stand for A by B and C by D, where B and D are non-zero. These two are what we want to multiply. From our understanding of rational numbers, we know that the answer would be AC by BD. So, we should define the equivalence class containing the ordered pair ACBD under this relationship as the result of multiplying these two. So, if multiplication of rational numbers is defined in this manner, it is exactly analogous to our intuitive understanding of rational number multiplication. Then we can see that this operator is commutative, is associative, distributes over the rational number addition, rational number 1 is the identity of this multiplication, whenever the product of two rational numbers is 0, either one or the other is 0 or both. Moreover, every non-zero rational number has a reciprocal, which is the multiplicative inverse. So, every non-zero rational number has a multiplicative inverse. This is at variance with the case of integers. Integers do not have multiplicative inverses. That is, integer multiplication is not invertible. Therefore, this algebraic system Q, along with the addition operation, the multiplication operation, the rational number 0 and the rational number 1, is a field. Recall the definition of a field from the module on algebra. Now, let us define the less than relation on rational numbers. We want to say that the rational number corresponding to the ordered pair AB is less than the rational number corresponding to the equivalence class containing the ordered pair CD. We want to define this relationship. When would be able to say this? We want to say that rational number AB is less than rational number CD, where A, B, C, D are integers, in particular B and D are non-zero integers. We will be able to say this precisely when AD less than BC, where this is the integer relationship. So, we will be able to say this precisely when AD is less than BC, integer AD is less than integer BC. You can readily see that this relationship is a linear order. Satisfies dichotomy and is transitive. So, we have now shown that rational numbers is embeddable. The theory of rational numbers is embeddable in set theory. But the way we have defined the rational numbers, integers which form a subset of rational numbers is not a subset of Q. That is, the way we have defined Z and the way we have defined Q, Z is not a subset of Q. We have used different definition techniques for Z and Q. But then, is this a contradiction? Not exactly. That's because we can define a set called ZQ as the set of all equivalence classes of this sort. Consider all ordered pairs N1 and the equivalence classes defined by them. So, the set of all these equivalence classes will form ZQ. So, they correspond to rational numbers in which the denominator is 1. An integer is precisely a rational number in which the denominator is 1. So, we define ZQ as this set. So, you can readily see that ZQ is the set of integers. They will function like integers within the set of all rational numbers. So we can see that ZQ and the set Z that we defined earlier are isomorphic. They have exactly the same mathematical behavior. Now we have an interesting theorem. We know that Z is countable. What is a countable set? We say that a set A is countable if there is a one-to-one mapping from A into N. Now, how do we know that Z is countable? Consider the set of all integers. So, integers go on both sides of 0. We have the positive side here and the negative side here. We should devise a way of counting these integers. So you should be able to say that this is the 0th integer, this is the first integer, this is the second integer, and so on. You count only using natural numbers. So if you count in this manner, 0 followed by 1, followed by -1, then 2, then -2, then 3, then -3. If you continue in this manner, then you can readily see that we are defining a one-to-one mapping from the set of integers onto the set of natural numbers. So we will be threading the integers in this fashion: 0 to 1, 1 to -1, -1 to 2, 2 to -2, -2 to 3, and so on. So if you thread integers in this manner, you find that every integer will be threaded together. We are giving one particular ordinal position for every single integer in the enumeration that we make. So we are enumerating the integers. In this enumeration is built in the one-to-one mapping from the set of integers onto the natural numbers that we talk about. Therefore, the set of all integers, namely Z, is countable. You can count them using natural numbers. What about Q? First of all, let us consider one quadrant. That is only the non-negative rational numbers. Let us first show that the set of all these are countable. But we will start off with all ordered pairs of natural numbers. So ordered pairs of natural numbers would be 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 1, 1, 1, 2, 1, 3, 1, 4, and so on. How would we enumerate all these ordered pairs? We could thread them together in this manner. Let us say you start from 0, 0, then we come to 0, 1, then to 1, 0, then to 2, 0, 1, 1, and 0, 2, then 0, 3, 1 2 2 1 3 0. Here of course we would have 4 0 as well. So if you thread the ordered pairs in this manner, you can see that every single ordered pair would be in this list. That is, we are giving an ordinal position for every single ordered pair when we enumerate them in this manner. So 0 0 is the first ordered pair, 0 1 is the second, and 1 0 is the third, 2 0 is the fourth, 1 1 is the fifth, 0 2 is the sixth, and so on. So if you enumerate them in this manner, what exactly is the technique we are using? We are enumerating ordered pairs in the order of the sum of the first component and the second component. For example, 0 0 alone stands for the class of ordered pairs in which the sum is 0. 1 0 and 0 1 correspond to the class of ordered pairs in which the sum is 1. Then we have the set of ordered pairs in which the sum is 2. 2 0, 1 1 and 0 2 all have a sum of 2. So we have sum of 0 coming first, sum of 1 coming next, sum of 2 coming third, and so on. So this is how we will enumerate the ordered pairs. Now you can figure out how to go from an enumeration of ordered pairs of natural numbers to an enumeration of rational numbers. So I am leaving it to you as an exercise for now. We will discuss it again later. That is all from this lecture today. Hope to see you in the next. Thank you.